Alright guys, welcome to our channel Code with Sunny, and in this video I will be talking about a famous interview problem, trapping rainwater. Okay, and its index is 42 and it is categorized as the hard type problem of the LeetCode. Okay, so one thing that is quite noticing over here, you can see that number of likes is like very much huge, like 12,869, and the number of dislikes is around 186. I think this problem is actually an interesting one because this problem has been asked in many interviews, and I will also recommend that every person that who is going to appear in any interview must have to solve this type of problem because this is a famous one and it gives a rough idea about what type of solution or what type of concept that you need to study about. And this problem is like a mixture of all of that. You can have a brute force solution over here which works in O of n square time. You can have a O of n time O of n space solution, and you can have a O of n solution, O of n time solution, and O of one space solution. And the tags that are associated with this problem is like you can use a data structure called stack. You can use a concept like dynamic programming, and like dynamic programming for prefix sums like that. And you can also use the stack as I've already said. And also you can have a brute force solution, the only one thing that would remain in rest of the cases. Okay, so what you will find in this video is that I'm talking about first I will talk about O of n solution, O of n time, and a space solution. Then following that I will be talking about O of n time and O of one space solution, how we are going to optimize our O of n space to O of one space. Okay, so moving further, I will first talk about, that is the very first I will talk about the explanation of this problem, then we'll together move further to build up the best solution for this problem. Okay, so let's move further. Given a non-negative integers representing an elevation map, okay, where the width of each bar is 1. Now we have to compute how much water it can trap after raining. Okay, so you can see that the term like raining is like a infinite amount of water that we are going to pour over these all the bars. Okay, so consider this like a heavy rainfall that has been occurred, like a huge rainfall, and like we have some walls that is placed over each coordinate, x coordinate you can also interpret in that way. And after heavy rainfall you are going to determine how much water is going to trap between these walls. Okay, so with respect to that, we would be given a, you can see a heat array, heat of the walls. You can also call it as bars. You can see if a heat of I is 0, you are going to say that there is not a wall. Okay. Otherwise, there is a wall of particular heat that will be given to us as an input statement, and we need to just output the total number of that is amount of water that is going to be trapped between these walls. Okay, so how we are going to do that? So I'm not talking about that right now. So let's talk about the constraints now. You can see that n is like heat dot length, and the maximum value of this n is like 3 into 10 power 4. So it gives us the idea that O of n square solutions is never going to pass. Okay, so we are not going to talk about that. So we are going to talk about either O of n solution or O of n log n solution, but here I don't think that O of n log n solution can be like we cannot have a O of n log n solution. We can have a O of n solution. Like if O(n) solution, if we have the O of n solution, then why not we would try for that rather than doing O of n log n solution, right? Okay, so we'll be talking about O of n solution, and every particular wall heat is like 10 power 5. Okay, so let's move further to first understand this problem, then we will together find out the best and utmost good solution for that. Okay, so let's move further. Okay, so guys, you can see a particular orientation of the walls that I have made over here. So if you can feel that after heavy rainfall, let's talk about how much water is going to be filled at this position. Okay, at this position. So you can see that that is I'm talking about water is going to be filled like above this one, like some amount of this is going to be filled. Okay, above this wall. So how we are going to find it out? You can see that you need to find out first that if I'm talking about this wall, that is whatever the walls that are present to the right of it, that is at these positions, You need to find out what is the maximum height of wall to the right of it. You can see that the maximum height of the wall to the right of it is this one. And if you're also going to find out the maximum height of the wall to the left of it, and it is about this one. So after heavy rainfall, it is obvious that water is going to be filled up to like this position. Okay, so it means that all these empty spaces is going to be filled by water. Okay, so this gives us the idea that for every position of the wall, what we are going to do is like we are going to find out what is the like a right max height of the wall of the with respect to current position. Okay, so if I'm talking about this position, you can see that the if you're trying to find out that wall which has the maximum height to the right of it is this one, and the maximum height of the wall to the left of it is this one, then your answer would be like minimum of this one and this one. So in other words, if you try to write down the statement for a particular ith position, you are going to find out that is minimum of, so let's call it as P as the prefix maximum of heat of the walls. So you are going to find out P of I minus 1. So it will give us the value that is all the that is the maximum value of all the prefixes of the heat of the walls. And that is I'm talking about the ith coordinate, right? Ith wall. And you are going to also find out S of I plus 1. That is the maximum value of heat of the walls of all the heat of walls to the right of it. Okay, if I'm talking about the ith wall. So you need to find out the min of this one. So if this has the value, let's say called x, then the amount of water that is going to be filled to the that is going to be filled for the ith position of the wall would be like x minus, and it should be like that is the current height that is the current height of the wall you are also going to account for, that is x minus h of I, where h is an array of height of the walls. Okay, so this is your answer. Okay, so there might be possible that you're not going to get the like x is not always strictly greater than, or like x is always not going to be greater than or equal to hi. So you need to take the maximum of this one and this 0, because it might be possible that the current wall is the maximum height of the wall among all the other walls. Then you are always going to get like x value of x, which is the minimum of prefix of I minus 1 and suffix of I plus 1. Then you are always going to get some negative value. Since the value is negative, it means that water that is being going to stored is like of negative 1, which is not possible. That's why we are going to take the maximum with this value 0. Okay, so this is the concept, and if you follow this concept for every position of the wall, then you are going to get your answer in O of n time and O of n space. The very first solution that I have talked about. You can see that this is the very first one. It has runtime 8 ms and it consumes this in memory. I don't think this is the best solution, because we can have a O of n time and O of 1 space solution also. I will talk about that later on. But now let's focus upon this short solution. You can see I have n as height dot size and answer as 0, and this is the prefix maximum of height of the walls, and this is suffix maximum of the height of the walls. Okay, now the concept is very much simpler. First I will use dynamic programming to find out the prefix maximum, suffix maximum, and I am going to do this in only one loop. You can see I have iterated for I equal to 1 and less than n, and I have calculated prefix max of I, this one, and I have also calculated the suffix maximum of I. That is, if I will talk about suffix max of I, it means that for all the walls, that is maximum of or maximum value among all the walls starting from the nth wall and ending up to the ith wall. Okay, and if I'm talking about prefix max of I, then it means that this value is equal to maximum value among all the walls starting from wall 1 up to the wall I. Okay, now what would be our answers? Our answer would be sum of all the like waters, okay, that is being accumulated over the over the walls. So if I'm talking about the very first wall, or let's talk about the any ith wall, our answer would be like min of this one and this one. First I will find out the minimum. It means that the minimum height to the left of like all the walls to the left of it and all the walls to the right of it. We'll find out the maximum among left walls, all the left walls among all the right walls, and I will then find out the minimum among these two values. Okay, why I am going to try to find out the minimum? You can see that water is going to be accumulated up to the minimum position among all the like among the two values that I have found now. Okay, so what would be amount of water that is being accumulated over here? Would be max of 0 and that value that I found now minus height of this current wall. Okay, so as I've already explained why I've like put it minus, like why I put it the value equal to 0. So after for answering a particular wall, you can easily see that I need to subtract the height of the wall also, because water is being accumulated at the top of the wall. Okay, so and return the answer finally after iterating for all the walls. Okay, so this is your answer for this is a solution for O of n time and O of 1 space. Not O of 1 space, sorry, O of n time and O of n space. Now I'm going to talk about this solution, which is O of n time and O of 1 space, and this is awesome. So let's move further to understand this solution. Okay, so let's state it out clearly that we are going to use a two-pointer technique. So in this case, what we are going to do is we are going to maintain two pointers like L and R, where L is going to start from the first wall and R is going to start from the last wall. Okay, so you can see that starting L is over here and R is over here, and we are also going to maintain the left max and right max of the walls. So initially left max. Okay, so let me write down clearly LM and RM. Now, the following condition that I'm first writing it down, then I will explain it how it happens over here. So if LM is going to be like less than RM, what we are going to do is we are going to increment our answer by LM minus height of this L. Okay, otherwise we are going to increment our answer, else in the else condition, we are going to increment our answer by RM minus H of R. Okay, note that we also need to increment our pointers, right? In this case, we are going to increment our L, and in this case, we are going to decrement our R. Okay, now why this happens and why we are going to follow this condition? This is going to be important to understand it right now. Now you can see that in this case, L max has height strictly less than the R max. You can see it means that we need to go over this position, and we need to answer for this case. You can see that if we are incrementing this L and adding out the answer, it means that we have already answered for this wall. Now why we are going to process for this L pointer, why not for this R pointer? The reason is very simple. As I've already said, if we are talking about this ith wall, what we are going to do is we are going to first find out the maximum among all the left walls maximum height and maximum among all the right walls maximum height, then we are going to find out the minimum, right? Now since we are processing left max and right max from their respective ends, and at a particular position if a left max is already less than the right max, it means that we need to process that left wall. Okay, that is giving the following output. Output is L max less than R max. Then we are going to process the L. Otherwise, we are going to process the R. Now consider this case. If this wall is processed, now we need to talk about which wall. We need to talk about this wall. So let me erase this one. Okay. Now we are talking about this one, and R is over this one. You can see that L max, our L max is going to change. L max is going to point out this position right now. Okay, so this is Lmax and this is Rmax. Now you can see that Lmax is like strictly greater than this Rmax. It means that we need to process this wall. Okay, now we can also prove it by contradiction, right? So suppose we are going to prove answer for this wall. If we are going to answer for this wall, it means that you need to increment your answer by this condition. Okay, so you need to increment your answer by this condition. It means that LM is the minimum value among all the left walls, and first you need to find out the maximum among the left walls and maximum among the right walls. Then we are going to find out the minimum, right? So if we are going to account for this LM, it may be possible that for answering this wall, that is, I'm answering for this wall, in spite of this wall, according to the optimal condition, Okay, we need to answer for this wall right now. Okay, but we are answering for this wall, and we are just proving it by contradiction that answering for this one is not optimal over here because Rm is going to be like less than this Lm. Okay, so suppose we are answering for this wall, so it might be possible that there exists some wall whose height is going to be greater than this one. Okay, so in that case, our answer would become wrong. Okay, because we need to just figure it out that R max comes maximum over this position. Okay, so what we are going to do is every time we are going to just move further for that wall. That is your answer for that wall whose value is going to give us the minimum. That is when Lm is going to be less than Rm, we need to talk about this L pointer. Otherwise, we need to talk about the R pointer. And this is like optimal case. Okay, so let's move further to code it out as fast as possible. You can see that here I have runtime was 4 ms and faster than this one. Okay, so the solution is like very much simple. Initialize answer as 0, L as 0, and R as heat dot size minus 1, and L max and R max both as 0. And iterate when L is like less than equal to R, find the L max and find the R max. Now, if L max is less than R max, you need to increment your answer for that wall whose left maximum is like the less than the R maximum because we are going to stop at this one. Okay, so you can see that I will increment my answer is this value and increment L also, and in else part do this one and return the answer. This is like optimal one. So if you have any doubts, do let me know in the comment section of the video, and I will ask the viewers to like this video, share this video, and do subscribe to our YouTube channel for latest updates. Thank you for watching this video.